This will be various light wave problems, like my titles. Problem number 2, we got 2 plates of flat glass lie on top of each other. One end is slightly raised. 670 nanometer light is incident upon it. 28 dark lines are observed, including 1 at each end. What separation is required? A lot of times it's interpretation that's of issue. So problem number 2, we basically have a plate of glass here. We have another one that is sitting something like this. It's about as good as I can draw it. We have a dark region here. We have a dark region at each end. And there's 28 total. There's 28 dark lines. Okay, I'm not going to try and draw those in. Because there's 28 dark lines, and that's actually, I probably should consider it looking from above here, looking down, but that doesn't really matter. With 28 dark lines, how many orders is that? Well, it would be 27 orders, because with 28 lines, there's 27 gaps. So 27 subsequent regions, spacing from one dark line to the next. All right, and we have our light coming in into this, and the first bounce is really here. This is the one we're interested in. It goes off like this, and the second bounce is at this interface here, and the part of that ends up passing through and going out again. So we have n is, well, inside here, n is equal to, it is the index of refraction for glass, so it's probably about 1.5. It's not given in the problem, but it turns out it doesn't really matter. And here is equal to 1, and then n is equal to, say, 1.5 again, something like that. In any case, the reason I'm even doing that is because I want to consider, is there a phase change here or not? Slow to fast. So this is no delta phi. Here, in this one, we're going fast to slow. So here we have delta phi is equal to lambda over 2. Seen that before, haven't you? So we have a total phase change of lambda over 2 from the bouncing. Therefore, the concern is that twice the thickness has got to give us lambda over 2. And that is incorrect because I got myself confused. We're looking at, see, something, this is a good point to make. We're not looking for constructive interference now. We're looking for destructive interference, dark lines. All right, so a dark line is going to occur when the total, here, big picture, total delta L, total path difference is equal to lambda over 2. That's how much total difference we need, so it destructively interferes. It cancels out. But delta phi is equal to lambda over 2. Well, that does it. Those are the same. So this phase change that occurs here produces the amount of phase change we need for destructive interference. So the path difference then, therefore delta L, the path difference, which is equal to 2t, is equal to some multiple of a wavelength. All right. So one wavelength path difference would do it, 2, 3, 4, etc. In fact, there's 27 orders, so there's going to be all those different numbers. But what we need to do here is figure out how much this was raised. So basically, I'll call this y. What is y? The amount that one is raised. The separation. So basically we're going to solve for the thickness. We're going to solve for the thickness to satisfy this condition. So T is equal to m lambda sub n over 2. But lambda sub n is air, so that's just equal to m lambda over 2, which is equal to 27. Lambda is 670 times 10 to the negative 9 divided by, that's 27, divided by 2, which gives us 9.05 times 10 to the negative 6 meters, or 9 micrometers. And that's how thick, or how much one side has to be raised to get 27 little, actually a total of 28 dark lines.